working on for much of the last 3, 4, 5 years is this whole computing curriculum thing. So as part of the team who drafted the new, still call it new, the new national curriculum for computing, and have been involved in a lot of the implementation projects since then. Show of hands, if you'll forgive me, who here is teaching computing themselves? Oh, splendid. Who here is teaching computing in their schools? Okay, that's great as well. Okay, so some of this, I hope then, is going to be particularly relevant to you folk. Slides are all online. I'm hopefully making a recording of this. We'll see how that goes. And the project that I'm going to talk about, this Project Quantum thing, is also details online. I'll put those references up at the end of the deck. So our friends at Ofsted, let's hear it for Ofsted. Okay, when they were... Thank you. Oh dear. Right, okay. Right, okay. So our friends at Ofsted, when they looked at the state of ICT education, which is a different curriculum, I know, different time, back in 2008 to 2011, saw that there was a real problem around assessment. And to make matters worse, they'd said there was a real problem around assessment of ICT 2005 to 2008, and we hadn't got any better. So what's the statistic there? In primary schools, assessment was no better than satisfactory, which now requires improvement in 53 of 86. And 42 of 74 secondary schools. So there was a big problem around assessing ICT as a subject. And it's worth wondering why that is. How come ICT was assessed so much worse than the other subjects on both the primary and the secondary curriculum? Anybody have any thoughts as to what the problem was? Why were we doing it badly? When I say we, I mean they, obviously. Okay, you don't have to. I think there are a number of issues, to my mind. Firstly, we tended to look at the output of the work, whereas most of the learning took place during the process there. And if all you do is look at the printout or the website or something, you can't see actually the learning that's taken place. If you have children working collaboratively in a team, which we know is a really good way of teaching ICT/computing, then how can you tell what one student has done and what the others have done? And there's also, back in the days of the ICT curriculum, we embedded ICT within the context of other subjects, and it was easy to look at the other subject, harder perhaps to look at the ICT. So we want to do computing differently. And I think there may still be challenges when it comes to assessing computing. We have a statutory attainment target in the national curriculum. By the end of each key stage, pupils are expected to, know, apply, understand the matter skills processes specified in the relevant program of study. That's a relatively easy thing to see. This is what we should have taught. Have the children learnt that? We have a number of frameworks for identifying what the content of the program of study is. This is one which I put together for the primary curriculum, taking all of those bullet points in the national curriculum, breaking them down into 3 areas: computer science, information technology, digital literacy. I'd call those the foundations, applications, implications of the subject, and putting them into some sort of vague order from the easy stuff at the top to the difficult stuff at the bottom there. That said, how can you tell from the work that a child produces whether they can evaluate data? What are you looking for to show you that there is evidence that you can tick off that statement in the program of study? What do you look for to show that they can identify a range of ways to report concerns about content? It's there in the program of study. What sort of evidence would you convince you that a child could do that? My friends Mark Dorling and Matthew Walker did a similar process for computing at schools, using the computer science bits of the curriculum only and producing this wonderful rainbow-coloured progression pathway for 6 strands of that. I'll give you a moment to copy down the relevant details. Okay, the problem around assessment is that what we're actually trying to measure, what we're actually trying to measure is the learning that has taken place in the child's brain. The connections between the neurons need to be there that weren't there before, or the connections between the neurons need to have strengthened in a way where they were previously somewhat weak, okay? You can't check that directly. It requires special equipment and special training, and the risk assessment for looking at a child's brain is going to be an horrendous one to fill out, okay? So all we have are proxy measures of this. You can't see directly that learning has taken place. What you can look for, though, is evidence of learning taking place. And we basically have a couple of options for this. One is the projects that they produce. give me a stack of their folders, show me the things that they've written in Scratch or Python or on PowerPoint or wherever, and I can look at those and try and work out whether they have learnt the things that I should have taught. And that's generally how we used to do ICT assessment when it was much more focused on the skills of using particular bits of software. An alternative approach, and that's what I'm going to advocate later on today, is this idea of questions, that we ask them a question about something, knowledge and understanding, possibly also skills. And from the answer that they give, we can say there is evidence there if they have learnt that thing. And I think this approach of asking young people, students, learners, questions about the things that we teach is more robust and is more efficient and is more reliable than just trying to figure it out from the work that they produce. That's not to say we shouldn't look at the work that they produce and encourage them to do that very, very well. But actually, if you want evidence of knowledge and understanding and possibly skills, then questions may be the better approach to take. Oh, you've got to be amused, by the way, by stock image of teacher. Notice the chalk in her hand there. That's what teachers do, isn't it? Okay, our friends at Ofsted say we should be doing lots of things with assessment. Teachers should be checking pupils' understanding systematically and effectively in lessons, clearly directed and timely support. And that's easier to do, I think, by asking questions than by going round and looking at their programs, their PowerPoints, their videos during the lesson. Asking the right question at the right time. And pupils are eager to know how to improve their learning. I think questions help with this as well, that I couldn't do this, but Miss taught me it really well, and now I can answer that question. By bringing it much more granular in terms of answers to questions, that seems to work. The Macintosh Commission on Assessment Without Levels was saying actually questions could be one of the best ways of going about doing this now. Rather than trying to come up with this sort of abstract notion of working at level 3, working at level 5, working at level 6, then why not say, here are a set of questions. If you can answer those questions by the time you leave primary school, then yeah, job done, big tick in the big box there of you've learnt primary computing. The Commission recommends the establishment of a national item bank of assessment questions to be used for formative assessment in the classroom to help teachers evaluate understanding of a topic and for summative assessment, enabling teachers to create bespoke tests for assessment at the end of a topic or teaching period. This is not too bad at GCSE because we have past exam papers to work from. Same story is true of A-level. Down in primary/prep, it's not too bad for English and maths and to some extent science because we've got old SATS papers and we've got old common entrance papers and we can draw on. For the rest of the curriculum, foundation subjects, primary key stage 3, it's hard because we don't have a bank of questions that we can draw on. And so what we're wanting to do with Project Quantum is produce that national item bank of here are some good questions you can ask about computing. Daisy Christodoulou, who's part of the Macintosh Commission, says put the questions first. Get the questions right, and then that guides the content of your lesson. That by the end of this lesson, by the end of this unit, the children in this class should be able to answer these questions. If you want to use some sort of notion of level or a vaguer statement of attainment, then have the questions which give an example of that as the thing which you work to. I want to give a number of contexts for this. Okay, firstly, there's this thing in software engineering called test-driven development. Anybody familiar with the term? Okay, so it's an agile development methodology which says, okay, you've got your software which kind of does what it's supposed to do. Client comes along and says, wouldn't it be nice if the software also did this thing? The first thing you do is not write the code to do the thing, but write the test to check if the code does the thing. By writing that test, it means you've got to have a really very clear understanding of what the thing is. That if this code passes this test, then the thing will be achieved, okay? It also means that you can check whether you've done your job properly in a very formal way if it's passed the test. What you do once you've written the test is put your existing code through the test suite, okay? Check that it doesn't do it already. If it does it already, then you don't need to do any more work because the code is already doing the thing that you've been asked to do, okay? Then go off and write the thing, all right? And spend your time doing that and doing that properly and so on. Then put the software through the test suite again, and the software should, of course, at that time pass the test of it does the thing now, all right? You then do a certain amount of more work of refactoring the code, making it more efficient, tidying it up, commenting on it, making sure that it's better integrated into the existing system, but it should still pass the test even after that sort of tidying up work. I think this works in our context too. We're asked to teach a thing to a group of students who already have some level of prior attainment. The first thing we ought to do is test whether they understand this new thing that we're being expected to teach. If they do, then job done, folks, yeah? If they can do it already, you do not need to teach it to them, because they can do it already. Okay, so move on to something interesting. Now, assuming that they can't do the thing, teach them the thing, and then test again at the end of that teaching unit, yeah? And they should, at that point, pass the test. If they don't pass the test, you've got to do a certain amount of debugging and make sure that they do pass the test, but test again at this point. If your senior leadership or your friends at the inspectorate say, can you show me that there is evidence of progress? Yes, they couldn't do it. I taught it. They can do it, yeah? That pretty much is it, isn't it, yeah? They learnt this because of my teaching. Don't just sit down at that point. You want to better integrate it. You want to make sure that they can do it more quickly or without having to think so much about it. But essentially, test-driven development, I think, works in our context too. Is this teaching to the test? Well, yes. But if the test is a good one, and passing the test is evidence that they have learnt the thing you were trying to teach, should we really be so worried about teaching to the test? Perhaps, perhaps not. Okay, Dylan William, who was Deputy Director of the Institute of Education, talks about this as using this sort of approach in the lesson itself. So you teach the main introductory bit, and then
when I was teaching regularly, I think the decision I used to make most often every single day was this: do I need to go over this one more time, or can I move on? How did I make that decision? I would make up a question on the spur of the moment. I would ask the class. 6 kids would raise their hands. I'd pick on one of them. They'd give me the correct answer, and I would say, good, and move on. Assuming the other 29 kids are now okay because they've heard one kid give me the correct answer, or that the other 29 knew it all along. So what we're saying is that actually that's a really bad basis for teachers' decision-making. Hearing from 1 or 2 kids who volunteered with an answer cannot be a sensible basis for moving forward. So what we're suggesting is that at least once every 20, 30 minutes, if you're going to make sensible decisions about what to do next, you need to get a response from the whole class. And we call these hinge questions. The idea is that we design our lessons with hinges in them. We don't design.
I'm going to stop there because we need to move on. Is anybody doing that already? Are you stopping after introducing a topic and asking a question to check that everybody's travelling with you? What do you do, sir?
I do think it's called in a nutshell, where the youngsters have to talk to each other about what they've learned. So number 1 tells number 2, and then number 2 fills in the gap.
And how can you tell if everybody's got it?
By then getting them to feedback to each other.
Really nice idea. Like that very much. Anybody else doing something similar?
Occasionally, but not regular enough, I suppose.
Oh, okay. What do you do? Similar sort of thing?
Similar sort of thing where you would sort of share ideas. You write down what you know, and then you share with the next person, and they give you yours, and you give them theirs, and they're teaching each other essentially.
Yes, peer instruction is, I think, possibly on the very next slide. We'll see what, can't remember what's on the next slide. Okay, so that's 2 contexts: test-driven development. Test beforehand, teach, test afterwards. Hinge point question during the lesson. Peer instruction was indeed on the very next slide. So they do this with undergraduates in the States. You have a question there as the starting point for your lesson. You put that up on the big display screen, and you get everybody to vote on their answer to that question, okay, or decide on their answer to the question. You then get them to talk to one another about that question and convince one another why that particular answer is the correct answer, and then do the voting thing with the audience response thing or whatever mechanism you've got there. Display those results up on the big screen, and then as a whole group, let's chat about why so many people in the room think it's that answer, what the actual answer probably is, try and get people in the room to convince other people to change their mind, and then and only then do you sort of explain what the actual answer to the question is. And this really does seem to work. So they've done the randomized controlled trial study. They've seen that where they try this method for teaching computer science and indeed other subjects, it actually produces better results than just sort of teaching the content, getting them to think about this beforehand, getting them to talk to one another, come up with convincing arguments. Baseline assessment: when the students enter your school, give them a test. See what they can do already. There again is your mark of progress that they couldn't do this when they came to the school. I've taught them, now look at what they can do. We have examples from the Learning Machine and elsewhere for this. Anybody entering the BEBRAS competition? International Beaver Challenge. Okay, so it's an international competition of questions on computational thinking, okay? Here is, there are multiple choice questions. The school, after school, the young beavers often play together to avoid quarrels and where to play. They throw a normal six-sided die. Decision is found according to this rule, which of those things would produce that particular outcome, getting children to work out the answer to this. And this is a big sort of fun competition. And I think Oxford University are running it for the UK now. Over in the States, multiple choice questions much, much more popular than they are here. They use this for big, high-stakes summative assessment. College Board, Advanced Placement, Computer Science Principles. The final exam is made up of, I think it's 40 multiple choice questions, including classics, such as a video streaming website uses 32-bit integers to count the number of times each video has been played. Some videos were being played more times than could be represented with 32 bits. Do you know which the first video on YouTube which hit that 32-bit limit was? Gangnam Style, absolutely. At which point we all want to break into something. No, let's not do that. Okay, so which of the following best describes the result of using 64-bit integers? So if your students can answer that, and questions like that, they're doing really pretty well, okay? So multiple choice has a lot of, it's not just simple recall questions. There's thinking going on here as well. You're making a change to your curriculum, you're making a change to your pedagogy, test whether it works. And the best way to demonstrate that this works is to do the control trial. For half of the students in the school, we're going to carry on as normal. For the other half of the students in the school, we're going to make this change. We're going to do this innovation. In order to check whether it's worked, baseline both, do the intervention to one group, test both groups at the end and see whether there's more progress from the group that had the treatment or compared to the control group. Okay, so lots and lots of context for this. To do any of those things, though, you need some good questions. Now, you can write those yourselves. It's not rocket science. Okay, it's kind of computer science, but it's not rocket science. You can write good test items yourself. But come on, we've got the whole of this internet thing. Wouldn't it be nice to collaborate on this? Wouldn't it be nice to work with other people, draw on the questions that other people have written? And so what we're trying to do with Project Quantum here is to crowdsource a national item bank of low stakes, high quality, formative questions for computer science. We have the great and the good working together on this project. So we have Tim Oates from Cambridge Assessment, one of the team who did the whole of the National Curriculum Review, advisor to ministers, great expert on curriculum change. We won't hold that against him. We have Professor Simon Peyton-Jones, Fellow of the Royal Society, inventor of Haskell, Chair of Computing at Schools. And we have Professor Rob Coe at Centre for Evaluation and Measurement Monitoring at University of Durham, who's one of our great national experts when it comes to assessment. And they're giving up their time to work on this project. And I think we're very, very fortunate to have such a fabulous steering group together. We're also working with the guys at Diagnostic Questions. Anybody using Diagnostic Questions in their school already? Okay, so it's a platform for multiple choice questions, really very popular in maths education. So go and talk to your maths colleagues when you get back to school. But we've got a platform already. Now, with such eminent people, you could easily have spent the first 6 months, year of the project trying to decide what platform are we going to use for this. We kind of made the decision we wanted to hit the ground running. DQ's site, Diagnostic Questions site, did much of what we wanted, so we went with them. In summary, on the one slide, what we're doing is free, okay? I'm not here to sell you anything, okay? It's free in the sense of free speech. You can take our questions and bring them into your Moodle or bring them into your Canvas or Firefly or whatever you happen to be using. They're there as images. You can use them for whatever purpose you want, and you can write your own questions, okay? It's all under a Creative Commons license. It's free in the sense of free beer. Did I just say free beer? Again, that you don't have to pay for any of this, and we're guaranteeing that for moving forward as well. It's also free in the sense of free kittens, in that really this is only going to be a success if you spend time on this process. We're not doing everything for you. If you want to use this, you've got to put in some of the work of making this part of how you teach in your school. Formative assessment, we're not interested in sort of big end of year tests. It's all done online, which works for us in the computing context. You can take the thing and put it into a PowerPoint deck, as I'm doing here. But the idea is that they answer the questions online, which helps you with the marking. So you don't need to write questions. You don't need to mark their answers. All of that is done for you in the Diagnostic Questions platform. We want it to be high quality, but we're setting the bar for people writing questions deliberately low. As long as there are no rude pictures in there and the right answer is the right answer, we'll let the question onto our platform. But we're going to use the data to drive the quality measure. So if enough students are doing enough questions, will be able to tell that this is a good discriminating question. People who get the idea do well on this question. People who don't get the idea yet can't answer this question. So we're going to let the data drive the quality. And low stakes, this isn't for something, for admission into a school or public exams. The idea is that it helps you with your teaching. It guides the content of what you're trying to teach in the lesson, that at the end of this topic they should be able to answer these questions. It's a good way of measuring progress, as we've discussed, and it's also a really good way of figuring out what it is that students don't understand about computing. Here are some of the questions here. It doesn't work entirely well on the big screen from the back of the room, but we've got a very, very simple logo programming question. We've got a turtle. Which of these following shapes would the turtle draw if we ran that code? And we could do show of hands or whatever. I can't remember quite. I think it is shape B, but you may wish to disagree. We'll have a go at the next one together. So this is one of these Bebras beaver questions. The beaver family, you get a theme to these questions, have 3 mobile phones, but none of the batteries have any charge. Familiar in your house? It takes 1 hour to fully charge a mobile phone, but this does not need to be done all in one go. The beaver family only have 2 mobile phone chargers in the house. What is the shortest time they need to fully recharge 3 phones? I'll give you a few minutes to think, no, a few seconds to think that over. I'm going to ask you in a moment to call out your answer, A, B, C, or D. Okay, I'm going to do a countdown from 3. When I hit 0, I want you to call out one of those 4. Okay, you've got a 25% chance of being right, even if you don't know. All right? Okay, here we go. 3, 2, 1, 0. I'm hearing B's and C's. Okay, so we could, if we had more time, go through, try and convince one another. Do you want to see what our survey said? What did children say in response to this question? Well, 45% of the students who answered this question opted for answer B. So for those of you who picked B, you're in very good company there. Regrettably, you are wrong, okay, in that answer C is correct, because, there's some clever recipe you can do about charge the first 2 for half an hour and then swap one over. You can work it out for yourselves, okay? The interesting thing about the DQ platform is not only do you choose one of the answers, but you give a reason for your choice. So these are the sorts of answers that people gave for the wrong answer. For answer B, 1 hour equals time it takes to fully charge 2 phones, can charge at the same time, so 1 hour frees up a charge for the last phone, which would take an additional hour, which is, I suspect, how the B people were thinking, okay? We can also see explanations for answer C. This is classic, so this is Python code. We do the same thing, okay? So A is 20, B is 10, A equals B. What are the values of A and B? Okay, 3, 2, 1. 1A. Thank you, David. Okay, is anybody else in the room programming in Python? Okay, don't worry about it. Don't feel bad about not programming in Python. Other languages are available. Okay, the answer is A. But we get a lot of students answering C. Not quite as many as answer A. We're fortunately at the point where this is very evenly spread between all 4 of those answers. But answer C is a really popular one because 20 plus B, 10 is 30, and B is 10 already, so it would be A equals 30, B equals 10, which is a reasonable argument to give if you've been taught that variables are like shoeboxes, because you take it out of one and put it into the other. Variables are not shoeboxes. They're named locations in a computer's memory. So we're seeing already with the quantum questions where some of the misconceptions lie, and we're kind of working out why there are misconceptions. What's wrong with this HTML code, or which of these HTML, which of these is correctly formatted HTML code is another example. We want people in schools such as yourselves using these questions. As I say, you don't have to pay for this. You can use them in whatever way you want, okay? So please do have a go with them. What's the worst that can happen, folks? The more people we have using these, the more we'll be able to learn from the data. But it would be lovely if some more folks were willing to write questions. If you're writing questions to use with your class, do consider putting them on the Diagnostic Questions platform so others can use them as well. What makes a good question? Oh, well, there's more to assessing whether somebody can program than just being able to write a multiple choice question or answer a multiple choice question. But this middle block here from Hazan Lapidot and Ragoni's ways of testing programming, all I think can be done using multiple choice. We're looking for ones which don't get in the way of your lesson. I could ask you a question which would take you half an hour to work out, and you might still not get the right answer. I think I could. Yeah, you might just guess at that point. We want ones which you can do fairly quickly without it getting in the way. Key thing for a good question is it shouldn't be multi-step. It should be one where the answer tells you whether they've got that one idea and where the wrong answers tell you exactly what the misconception is. If you put too many steps into the same question, you can't tell where it went wrong, okay? Other ways of doing that. You should be able to learn what the misunderstanding is from the incorrect answer, and you shouldn't be able to get the correct answer while still having the key misconceptions, okay? Yes, I know it's multiple choice. I know they can just guess, okay? But we can take that into account in the data analysis. And we're trying to persuade folks to write ones which get a higher order thinking skills, not just which of these is the correct definition of algorithm, which we have quite a few of in the platform as things stand, okay? So, how's time? Yeah, okay, it's 5 more minutes. Okay, let's just do a couple more questions. What do you think about this question? Here are 2 images of programming code. Identify the programming code. Identify the true statements. Examples of Java, Scratch, Python, examples of subprograms. Okay? Talk to a friend if you're not sure. Or the person you're sat next to if they're not your friend. You know, make friends. Okay. Okay, let's do calling out again, please. 3, 2, 1. I had B's and C's, yeah? B, okay. Well, one of them is Scratch. But they're not both examples of Scratch. It must be D, mustn't it? You don't need to know anything about Scratch or anything about Python to be able to work out that they're not written in the same programming language. And thus the only possible answer here is D. Yeah? I give this to my class and say, oh, wow, look, 30 out of 30 know what a subprogram is. No, 30 out of 30 can correctly game multiple choice questions, which may not be a bad thing. But, you know, we're not learning what the students know about programming. This is a different one, okay? Same STEM, but different distractors, very different distractors. Again, by all means, talk. Okay, 3, 2, 1. C. I heard a B. Okay. Who was the C person? Persuade me why.
Because both pieces of code are doing something, so therefore they're both procedures.
Thank you very much. Who was the B person? Persuade me why B.
Well, I thought X was a procedure, and then I thought, I don't know why, really, but it looked like a calculation to me.
That's a very good way of thinking about that. Okay, so my argument that you have to know what a function is in order to be answer the question, not entirely true, but you know, you had some mental model of what a function must be from your background knowledge of maths, I guess. Yeah, absolutely spot on. Well done. Okay, so because we make this distinction between procedure and function, that a procedure can do something, whereas a function only returns a value to us, which is exactly what the difference is between x and y on this occasion. So this, I think, is a much better question than the previous one. Here's another example, okay? So explain who knows the bubble sort algorithm? Okay, bad luck. Let's see how you get on with the question about it. Okay, explain how the bubble sort algorithm works. Results should be in ascending order, lowest to highest. Here is a list of numbers. What does the list look like after the final pass of a bubble sort? Three, 2, 1. Yeah, okay. Did any of you actually do a bubble sort on that list? You just spotted that B was the list in order, didn't you? Yeah? So this is a test of can you tell whether a list of numbers is in order, which is a relatively low order skill, yeah? This is not a test of whether you understand the bubble sort algorithm. Yeah? So this, I think, is a bad question. This is a good question. Making you do this is a little bit cruel, and it kind of depends on your definition of the bubble sort algorithm, because this notion of there's a flag in there which tells whether we've swapped or not. But you can't answer this question unless you've got a pretty good knowledge of how we would set a flag to show that we've not actually done any swaps within a pass-through the bubble sort algorithm. We get lots of data. You, if you're using this with your class, will get data about your class. But you can go into any question on the Diagnostic Questions platform and have a look at what students have responded to it. Yeah? A question where you're getting 100% all giving exactly the same correct answer, that might be very positive and affirming for the students who do that, but you're not getting any information back from setting a question like that. A question where nobody gets it right, or less than 25%, which is worse than monkeys would do, get it right, might be too hard. Something somewhere in the middle is where it gets much, much more interesting. And so you can see from the Diagnostic Questions site, which questions students have found really difficult, which questions students have found very easy, and bring those together into quizzes and setting a quiz for your class. And of course, you get to see the explanations that they give. The student who gives the wrong answer can see the correct explanations they can learn from doing these questions as well. We have, or rather our friends and colleagues at Diagnostic Questions have development work planned over the summer. So at the moment, you get this sort of very sort of general sort of scoreboard type thing of this is a question here where only 14% gave the right answer, which is significantly worse than monkeys would do on that question. We've got a similar sorts of things going on there, where there must be some sort of big misconception thing going on. What we're getting to is a dashboard which looks much more sophisticated like that. And this relies on something called the RASH model for item analysis or for human measurement, which says for every, we have some spectrum of ability from the least able, those who do worst on these questions. I think able may not be the right word, to the most able, those who do best on these questions. And you can tell then, so for our most able, those who are doing very well on a bank of questions, most of those gave the correct response, A. Our least able, very few of those gave the correct response, A. And so we can do that. This is a good question to discriminate at this bit of the ability range. And then some of the statistics are on it, number of times it's answered, number of times it's been used in a quiz. And then this sort of abstracted notion of how hard this question is and how high quality the distractors are and what proportion of students appear to have just guessed on this. So all of this is coming for September, but it's there, ready to use now. We're kind of out, yes, we are out of time. I've gone way over. So contact details up on the slide there. If you want to see the slides again, that's the URL, bit.ly/quantumisp. More about the project, bit.ly/projectquantum. As I say, it's free. Please have a go at this. Photo on the picture of the slide being taken there. David, do I have time to answer one question?
Absolutely.
2 questions? Okay, as long as it's not a multiple choice. Okay, anybody?
Yeah, I'm kind of trying to rewrite an assessment procedure from year 1 to year 6. And there are so many available out there that people are trialling and doing. I'm almost at a loss now as to how to go about it. Where would be a good place to start?
Okay, how are you using a particular scheme of work?
No.
Fine,
it's
all right.
I mean.
Okay, well done.
And it's totally based
Yeah.
on learning outcomes.
Yeah, okay, so, I mean, I'm biased. No, I'm a late convert to this, to be fair, because stuff I'd written 3-4 years ago, I was saying, get them to write blog posts, get them to annotate what they've learnt during the work, and then you as the teacher just need to go in and look at what they've said they've learnt from this unit of work. I'm no longer of the view that that's the best way to do this. I think coming up with a few questions to ask even your little year ones at the end of the topic, and then you'll get from that, they know how to do this. Or, yeah, they've come to those lessons.
Would that serve as evidence to an Ofsted inspection?
Oh, gosh, yes.
So it all comes back to
No, absolutely. And, have a look at the stuff which Daisy Christodoulou has written. Have a look at what the Macintosh Commission have written. Ofsted's rule is that any assessment has to be in line with the school's assessment policy, okay? So you can't go off-piste unless your head teacher says, well, computing is different. Computing we assess in an entirely different way. That's okay. You can do that as long as it's written into the policy. But follow the rules in your particular school. But no, they couldn't do this. I taught it. They could. That's as much evidence of progress as our friends at Ofsted would ever be able to expect to see. Okay? And if the things that they can do at the end are getting harder and harder as they work their way through the school, even better. Tim Oates is really very good about arguing how curriculum and assessment really do need to go hand in hand. He calls this curricular coherence. And I think he's right. And of course, what we did with the national curriculum was sort our curriculum and just forget about assessment. Well, let schools choose. Okay, that was one question. Anybody else? Burning questions? Okay, I'm going to be around for a little bit of the morning, so come and catch me at break time and talk about some more of this. Thank you very much for your time. Thank you.